Hello students, welcome to my class on operating system. Today I will discuss deadlock. After going through this lecture, you will be able to understand why the deadlock occurs and how we can solve the problem of deadlock. Now, deadlock is a very well-known term. Deadlock occurs in our real scenario also. So you can understand that while we are traveling through the roads, so it may happen that due to certain scenarios, so suppose consider we are traveling through a road. So the roads are like this one. Okay, so this is a one-way road, and another road is crossing like this one. And now the problem is that due to the improper traffic control signal, or due to some problem in the traffic system, so it may happen that some cars are coming through this road and this entire road is blocked, and some set of cars are coming from this road, this entire road is blocked. So we assume at least only one car can go through this road. Again, some cars are coming from this road and some cars are coming from this road. So what happened when all the cars are there in these points? So no cars can move further. All of them get stuck. So this is a problem, is called the deadlock. So this car, so let us numbering it. This is car number 1, this is car number 2, this is car number 3, and this is car number 4. So car number 1 cannot move further because all the roads are blocked, all the traffics are there. Car number 2 cannot move further, so all of them get stuck in a single position. So this situation is called deadlock. Fine. Now this deadlock occurs also for the operating system. So now let us understand why the deadlock occurs for the operating system. So in terms of the process, you know that what is a process? Process is a program in execution. So let us say this P1 is a process and P2 is another process. Fine. Now the process P1 wants to execute with the set of some resources, help of some resources. So let us say R1 is the resources and there is a single instance of the R1 resources. Now what do you mean by the instance of the resources? So this is called the instance. Now what do you mean by the instance of the resources? The instance of the resources means that R1 is the type of the resources and one such type of resource present in the system. So let us consider USB. USB drive is the type of the resources and one USB port is available. So number of instances 1. Now what will happen? Suppose P1 wants to access this resource R1. P1 cannot complete its execution until and unless it is getting R1. And P1 also another resource R2 is held by P1. So another resource R2 is there which is already assigned to the process P1. Fine. So I have two resources, one is R1 and second one is R2. R2 is already assigned to P1 and P1 is requesting for R1. Okay. Now what will happen? Consider another process P2. P2 already have the resource R1. So this resource R1 is already assigned to P2. But P2 is waiting until and unless it is getting R2. Clear? So I have two resources R1 and R2. R1 is assigned to P2. So better if we draw the diagram like this one. This is my P1, this is my P2, and this is my resource R2, and this is my resource R1. R1 is already assigned to P2. R2 is already assigned to P1. P1 is waiting for R1 and P2 is waiting for R2. So this is a better diagram. So in this case, you can see that P2 cannot complete its execution until and unless it is getting R2, and P1 cannot complete its execution until and unless it is getting R1. So here both the processes are waiting for each other. So this scenario in terms of the operating system is called a deadlock. Okay. So deadlock is very important problem of the operating system, and to solve the synchronization problem, sometimes or improper use of the synchronization algorithm may cause the deadlock, or the if the process wants to get the access some gets access some resources and the resources are not available, in that case also the deadlock may occur. Fine. So this problem is called the deadlock. So we are writing it deadlock. Fine. Now the deadlock, there are some conditions. Fine. So those conditions are called the necessary conditions for deadlock. So how we can understand that whether the deadlock has been occurred in the system or not? So this can be understood by observing the necessary conditions. So there are 4 necessary conditions. So we will observe them, all of them, and then we can decide by observing those necessary conditions, we can decide whether the deadlock has been occurred or not. Fine. So now we will discuss the 4 necessary conditions for deadlock. So this is called the necessary condition. Condition for deadlock. Okay, necessary condition for deadlock. So this is very important, the necessary conditions for deadlock. So there are 4 conditions which are very much required. By observing those 4 conditions, we can decide whether the deadlock has been occurred for the system or not. So the first condition is called the mutual exclusion. So this is called mutual exclusion. What is mutual exclusion? I have already discussed in my previous lectures that what is mutual exclusion. If 2 processes P1 and P2 wants to access a common critical section, so there is a critical section CS, P1 also wants to access the critical section, P2 is also wants to access the critical section. So if P1 and P2 both wants to access the critical section, in that case what will happen? So both the processes cannot access the critical section at the same time. So either P1 can access first or P2 can access first. So let us put the numbering P1 and 2. So that means if P1 will access the critical section first, then the P2 cannot access, P2 will access after P1. So this is called the mutual exclusion. That means if 2 processes wants to access the critical section, then both the processes cannot access the critical section at the same time. They have one process at a time can access the critical section. So if there is any mutual exclusion, and if we cannot handle the mutual exclusion properly, then the deadlock will occur. Okay. So this is the one conditions for the deadlock. We have to observe for the mutual exclusion. If the mutual exclusions, if any critical sections are there, then we have to ensure that one process at a time will execute the critical section. This is the first condition. Okay. Now the next condition is called hold and wait. So that is another important condition for deadlock. So this is called hold and wait. Now what is the hold and wait conditions? The hold and wait condition says that if P1, so as I have drawn in previous diagram, so P1 holds the resource R2 and it is waiting for R1. So P1 resource R2 is already assigned to P1 and P1 is requesting for R1. Similarly, P2 is already holds the resource R1, but it is requesting for R2. So if there is hold and wait condition, that means if a process is waiting for some resources by holding another resources, then the deadlock will occur. So that is another conditions for deadlock. Now the third condition is called the no preemption. What is preemption? Preemption means we can forcefully take the resources. No preemption means if the situation is like that, if resource R2 is assigned to P1, that resource R2 cannot be taken by any other processes or by the operating system. If P1 release the resource R2 by itself, then only resource R2 can be released. So this condition is called the no preemption. That means forcefully the resource cannot be taken from any process until and unless the process will release the resource by itself. So no preemption is another condition for deadlock. So if any system the no preemption exists, then the deadlock will also may occur. And the last one is called the circular wait. So the fourth condition is called the circular wait. Okay. Now circular wait means, so here you can see that the process P1 is waiting for P2. So P1 is waiting for P2. Again, P2 is waiting for P1. So this type of waiting is called the circular wait. So if the circular wait is there, then this circle cannot be broken in future. So this type of circle can create the deadlock. Okay, so there are four necessary conditions for deadlock: mutual exclusion, golden wait, no preemption, and circular wait. And this is very important to note that if all the four conditions must hold, then the deadlock will occur. Okay, so that means if for a particular system, if we can check that all the four conditions are true, mutual exclusion is true, golden wait is true, no preemption is true, circular wait is true, if all four conditions are true, then we will definitely say that the deadlock is present in the system. So what we have to do, how we can solve the deadlock problem of the deadlock? We can solve the problem of the deadlock by avoiding any one of them. That means if all the conditions are true, so this is true, this one is true, this one is true, and this condition is also true. Of all four conditions are true, then the deadlock will occur. But if we can ensure that among those four conditions, if we can any one of them, if we can break any one of them, that means if we can make them false. Like if I can make hold and wait as a false, fine. So in that case, the deadlock will not occur for the system. Or if we can make the no preemption false, then the deadlock will not occur for the system. But mutual exclusion, remember one important point is mutual exclusion. We cannot make it false. It is not possible to make the mutual exclusion false. Fine, you cannot make it false. Why? Because if you make the mutual exclusion false, that means you have to allow both the processes P1 and P2 to access the critical section at the same time, which in turns can create the data inconsistency. Fine. So this is a very important problem, that mutual exclusion must be there. It is true. It must be true. It cannot be false. But above the mutual exclusion, there are four conditions, and if we can make any one of them false, then deadlock will not occur for the system. Okay. So now next I will discuss that how we can how we can check whether the deadlock is present in the system or not. Fine. So for that purpose, we will analyze the resource allocation graph. So you can so far you can understand that four necessary condition you have to so if you have system is given, you can observe for all the four necessary conditions, and you can by altering them while you are implementing your operating system, you can make any one of them false, and then you can ensure that for your operating system the deadlock will not occur. Fine. Now the next thing is that how we can detect that whether the deadlock is there or not. So to detect the deadlock, there is a strategy technique which is called the resource allocation graph. So what we can do, we can draw the resource allocation graph. Resource allocation graph. Fine. Now for the resource allocation graph, what we have to do, we have to draw a graph. Now as you know that a graph G is a set of vertices and set of edges. Now, before drawing this graph, we have to initialize what will be the vertices and what will be the edges. Now, here the vertices V can be what are the things belongs to the vertices? The vertices can be set of resources and set of processes. So all the resources and processes are identified as or symbolized by the vertex. And edges are of two types. One is called the request edge, and second one is called the response edge. Okay, response edge. Request edge means if a process is requesting for edges for some resources, then that edge is called the request edge. And if it is already assigned, so this is called the response edge, or sometime it is also called the assignment edge. Okay, we can write it also assignment edge. Fine. So those are the set of vertices and set of edges. Now let us analyze some problem. So consider there is a process, set of processes P, and they are P1, P2 and P3. Okay. Now there is also a set of resources R, which is called R1, R2 and R3. Okay. Now the thing is that R1 has one instance. So this is very important. The resource R1 has one instance. So as I have already discussed that what do you mean by the instance? R1 is the type of the resources and how many that type of resources. So for example, pen is a type of resources, and if I have one blue pen, one black pen, so I have two pen. So here the number of instances for the pen resources is 2. Fine. So in the same way, the like printer is a resources. Now I have a dot matrix printer attached with my system, and I have one laser printer attached with my system. So printer is my resources, and how many instance of those resources is attached with my system? One dot matrix and one laser. That means 2. Okay. So for the resource R1, there is a single instance. For the resource R2, there is 2 instances. For resource R3, there is 3 instances. Fine. So resource R3, okay, let us say resource R3 has 1 instances, and we take another set of resource R4. So this resource R4 has 4 instances. Okay. So what will happen? The process P, is P and R both are vertex. So P process can be represented by circle. So if there is a process P1, we will write it inside the circle, and the resources will be represented in terms of the rectangle. Fine. So here the resources, let us say R4, and how many instances are there? 4 instances. So draw 4 dots. So for each dot represent 1 instance. So in this way we will represent the vertex. And 2 type of edges are there, request edge and assignment edge. If it is a request edge, then in that case P1 is making, process P1 is making the request for a resource R1. Let us say there is a single instance of the resource R1, P1 is making request. So this edge will be from P1 to R1. But if the thing is like that, the resource R2 is already assigned to the process P1. So the assignment edge will be from resource to process. So 2 types of edges are there. This edge, that means the process to resource, this type of edge, this is called the request edge. Fine. And this edge, which is from the resource to the process, this is called the assignment edge. Assignment edge. So 2 types of edges are there. So using those edges and vertices, we will draw the resource allocation graph. So now I will show you how the resource allocation graph will help us to identify whether there is any deadlock present in the system or not. Okay. So we will consider, we will go through this example. So there is a process P1, set of processes P1, P2, P3, resources R1, R2, R3, R4, and R1 has one instance, R2 has two instances, R3 has one instance, and R4 has four instances. And the set of edges, which we can say E, so there is a set of edges E. And what are the set of edges? It will also be given that P1 is making request for resource R1. Okay, P2 is making, the process P2 is making the request for resource R3. Then process resource R1 is already assigned to the process P2. Resource R2 is already assigned to the process P2. Resource R2 is already assigned to the process P1. Resource R3 is already assigned to the process P3. Okay, so those are the set of resources. There are some edges are assignment edge, some edges are request edges. Okay, so now we will draw the diagram. So first let us draw the set of processes. So those are the set of processes. Fine. So we will write it P1, P2 and P3. Now there are some set of resources. So we will draw the set of resources. This is called R1, which is single instance. There is also the resource R2. We will draw it over here. R2 has two instances. There is the resource R3, which has single instance, and there is also the resource R4, which has four instances. Fine. Now we will draw the edges. Now what is the edges? As per the diagram, so P1, process P1 is making the request for the resource R1. Okay, so process P1 is making the request R1. So there will be an arrow from P1 to R1. Next, process P2 is making the request for R3. So P2 is making the request for R3. So arrow will be from P2 to R3. Now next, resource R1 is already assigned to the process P2. So there is one single instance, and this arrow will be from the instance. Okay, so we will take another color. So this R1 is already assigned to the process P2 as per the edges given over here. R2 is already assigned to the process P2. So there are two instances of R2. So one instance is already assigned to the process P2. Fine. Now there is another instance of the R2 which is assigned to P1. So let us say this instance is assigned to the process P1. And R3, resource R3 is assigned to the process P3. Okay. Now in this way, so you can see we can get a graph with the help of the set of vertices. We can draw a graph with the help of set of vertices and edges. And this graph is called the resource allocation graph. Now by observing this resource allocation graph, we can say whether the deadlock is present for this particular scenario or not. Now here you can see that for this particular scenario, how we can detect the deadlock is there or not with the help of a cycle. So in the graph, if there is any cycle then or the circular path, then we can say that the deadlock is present in that for that particular assignment. If no cycle is there, then we can say the deadlock is not present over there. So here we can see if we traverse from these edges, so here after reaching here the cycle is not completed, so we are not getting any cycle over here. So we can say that deadlock is not present for this particular system. Okay, so as no cycle is there, the deadlock is not present over there. So how we can say that by observing the resource allocation graph, how we can say the deadlock is there? If there is no cycle. Fine. So if there is no cycle, then we will say that deadlock is present for the graph. Fine. So here I will write the instance, that is, so no cycle. Fine. No cycle means no deadlock. No cycle, no deadlock. Okay. And if there is a cycle, then the deadlock is also present. Now in this particular graph, there is no cycle, so deadlock is not there. Now what we can do, let us modify, add some extra edges. So consider there is an edge like P3 arrow R2. That means process P3 is requesting for the resource R2. So if it is so, process P3 is requesting for the resource R2, so definitely there will be an edge from P3 to R2. Now if we add this edge, then you can see that we can traverse like this one. So if I start from P3, we can traverse like this, then we can move like this, P3, then we can move from R2 to P2, then from R2 to P2 to we can go R3, then from R3 again we can go back to P3. So that means there is a cycle. Fine. So we can move like us. There is a cycle present. We can construct a cycle. We can find out a cycle in this graph after adding this particular edge P3 R2. So that means we can move from P3 to R2, R2 to P2, P2 to R3, and R3 to P3. So that means there is a cycle is present over here. This cycle is there. So as there is a cycle, then we can say now for this particular resource allocation graph, the deadlock is present. Okay, so in the previous example, there is no deadlock as there was no cycle, but in this case, a cycle is there. So we will say that here as we are getting a cycle, so we can say that deadlock exists. Deadlock exists for this allocation. Okay, so this is one way to identify whether the deadlock is present or not for a particular system. Fine. Now in the next class, I will discuss that how to. So resource allocation graph will help you to find out the deadlock, but how to get out from how to get relief from the deadlock, how we can come out from the deadlock. So this deadlock detection or deadlock prevention, avoidance, those type of solutions we will discuss in the next class. So in the next class, I will discuss Banker's algorithm, which will help us to get out from the deadlock. Okay. Thank you for watching my video.